Tonight we want to prove that a prime power can't be a perfect number. And y'all, by prime power I mean this normal letter P, where P is prime and then K is just a positive integer. So K, I'll call it a member of the natural numbers, positive integers. Okay. Now let's talk about what a perfect number is. This is its definition. A perfect number is equal to the sum of its proper divisors, and a proper divisor is a divisor of a number that's less than the number itself. And of course, as in this example with 6, 6 is a divisor of itself, but the sum of its proper divisors is 6. And that's somehow or another that got called perfect in mathematics. The next one is 28, where you sum all these up, 1 plus 2 plus 4 plus 7 plus 14, all the proper divisors, and you get 28. Now, one thing to notice here, guys, there's some notation here called sigma notation, and I'll just use it right now. You may have seen it, but what it does, it's a function that sums up all of the divisors. So sigma of 6 is actually equal to 12, because 6 itself is also a divisor. So you would have 1 plus 2 plus 3 plus 6, which is 12. Okay, in a similar fashion, sigma of 28 is, and I'll write this for emphasis, is equal to 56. That's 2 times 28, right? Again, you guys can check this out right here. If you just tack on a 28 to the end of this, which is what sigma does, it does all the divisors, it's rapacious, then you get 28 plus 28 is 2 times 28 is 56. Now that leads to this definition of what we mean by a perfect number. N is perfect whenever sigma of n, the sum of the divisors of n, is just equal to twice in itself. Okay, now let's move along to the proof. Probably the so-called deepest part of this is writing down the sum of P of K, the sum of the divisor of P of K. The only divisors of P of K are other powers of P less than or equal to K. And if you reason through this, just that follows from the definition of a prime number. If there were other divisors that weren't in this form, P raised to some power, they would have to have a prime divisor different than P, but that violates the definition of P. So these are the only divisors of P of K, other powers of P less than K. This wouldn't be true if you had like a composite number like 8 to the third power. The only divisors of 8 to the third power wouldn't be 8 and 8 squared and 8 cubed. There'd be others, many others, 4 and 2, for example. So it's the difference between a composite number and a prime number is that a prime number has this kind of sleek sum of primes set up. Okay, now we're going to assume that P of K is perfect, and by this definition that we just derived, I guess, that means that sigma of P of K is 2 times P of K. So we're going to assume this and see if what happens. We're going to assume this is true and see what happens. Now, so sigma P of K is equal to 2 times P of K, which is equal to this result right here that we just spent a little bit of time on. Now, when you subtract P of K, when you subtract this P of K from both sides, I didn't write it in here, y'all, but there's a plus P of K minus 1 that precedes P of K, right? So that's where this comes from. Right here, I didn't write it in. You got to, it's hard to write down everything. But this is this right here, okay? All right, now, so we've got to this point. Now, a lot of you might already recognize that this is an impossibility. You've seen this this is something you can prove even by induction, I think. But if you haven't seen it, remember this is really a geometric series with a common ratio. Y'all, I'll call it CR, common ratio. Common ratio equal to P, okay? Or to get from one term to the other, you just multiply by P. So it is a geometric series. And you may remember that this left-hand side just becomes, the sum becomes P of K. Now, one way to remember this, and you can derive this, it's not too hard to derive this, but there's actually K terms here, right? This is P to the 0, right? All the way up to P to the K minus 1. There's actually K terms. And so the sum of this left-hand side is going to be P to the K minus 1 over, let me get some more space here, P minus 1. And y'all, this is a known result. I want to attempt to prove it here or go through it. You can write it forwards and backwards and you can get it to come out. It's a nice little proof. Forwards and backwards, subtract it, and you'll actually get this result right here. But we're getting this statement right here. Okay. Again, this is what I think is sometimes called a closed form. This left-hand side here is a closed form sum for this. This left-hand side here is a closed form sum for the left-hand side right up here. So we get this statement. And again, that's the supposition that P of K is perfect, okay? But watch what happens here. You could probably tell right now that this is impossible, right? See, because look, P of K, I'll just write it down. I don't think there's any reason to prove this. It's very clear. First of all, P of K minus 1 all by itself is less than P of K, right? But also we're dividing by P minus 1. Again, P of K minus 1, I'll just write off the side. P of K minus 1 all by itself is less than P of K. Strictly less than P of K, right? By 1. But you're even dividing it by another number, making it even smaller. So you see, this is impossible. Okay, so our supposition led to this impossibility, or some people would prefer to call it a contradiction. Okay, this is impossible or contradiction, whatever language you choose here. But how did this impossibility, what bore this fruit? Well, it's this supposition right here. We assume this is true. So what we have found is that I'll just write it down. Summation of our assumption here. Summation of P of K never equals. Now I'm being a little sloppy with the quantifiers here. I should be doing for all and there exists and all that kind of stuff probably. Okay, but I've shown that if we assume that it's true for any one of them, you get this contradiction. That means any other prime, who cares what the prime and what the power is, you would get this kind of contradiction. Okay, so I think that's a conclusive proof. And so we can write QED. All right, y'all. That is all for now. And let me know what you thought. I hope I said enough right here to show that this is the sum of the divisors, and it would be a conflict of the definition of a prime number if we tried to assume there was anything else in this list of divisors. Okay. All right. Thanks for viewing.